Hi, welcome to our face-to-face meeting for Stat 151. Today we're going to talk about some questions from sections 1.3 to 1.5. These are the sections that talked, remember, about the idea of conditional probability, independence between two random variables, and then applying some of the ideas from those to something called Bayes' theorem. So there were not a lot of questions on the discussion board this week. I'm going to start by just drawing attention to a couple of things, and then we'll talk about the one question that was posted on the discussion board. So the thing that I want to mention first of all is just that when we give this probability of A given B, it's a conditional probability. Just want to point out that when we talk about probability of A given B, sometimes another way that this is seen in terms of sort of regular language is the probability of A if B happens, right? So when we see the word if, we need to think conditional probability. Sometimes people think of that, sort of make the mistake of thinking that that is an intersection. But if I'm talking about the probability of earning an A in the course if you do all your homework, that's conditional on you doing all your homework. What is the probability that you get an A in the course? Not the probability that you will do both. Right, so that is just a first aside. When we define these probabilities, the conditional probability is the probability of A intersect B divided by the probability of B. Note that if we rearrange this, the probability of A intersect B is the probability of A given B times the probability of B. I mentioned this just to kind of reinforce this because often people have seen in previous courses the situation where if we have independent events and we're looking for the probability of an intersection, we can just multiply the probability of A times the probability of B. I just want to point out that really we can only do that if the two events are independent, because if the probability of A given B is equal to the probability of A, then what this means is that knowing what happens with event B, whether it occurs or not, tells you nothing about whether or not event A happens. So this will only be true if the probability of if A and B are independent. So probability of A intersect B equals the probability of A times the probability of B if and only if A and B are independent. So just kind of reinforce that. Because even after this section, often we'll see people multiplying probabilities when we don't have independent events. So that's something to just be really careful about, not to fall into that trap, because I think a lot of people have seen those types of problems before where they were working with independent events. Okay, other thing I just want to draw attention to, because I think the book does not draw much attention to it, is something called the law of total probability. It's kind of buried in the book. But the law of total probability is extremely useful. What it says is that if B1, B2, up to Bm are mutually exclusive and exhaustive, so what does that mean? Mutually exclusive and exhaustive means, first of all, mutually exclusive means only one of them can occur, and exhaustive means that at least one of them must occur, right? So really what this means is that exactly one of these events must occur. Then we can think of an event A as the intersection of A with the first event, B1, union the intersection of A with the second event, and so on through the intersection of A and the nth event. And so what this means is that if we need to calculate the probability of A, then we can do it by figuring out the probability of these intersections. Because these B1 through Bm are mutually exclusive, there won't be any intersections between these events. So we can add probabilities of A intersect B1 plus the probability of A intersect with event B2, and so on, up through the probability of A intersecting with B sub m. And then if we have independent events, we could multiply probabilities, but in general, this would be the same as the probability of A given that B1 occurs times the probability that B1 occurs plus the probability of A given that B2 occurs times the probability that B2 occurs, and so on, up through the probability of A given that event B sub m occurs times the probability that B sub m occurs. And as I say, this is an extremely useful thing. We're sort of partitioning the sample space into these mutually exclusive events, and it gives us a nice way of working with these. An example of one of the book problems that works with this would be 1.3-6. You can use the law of total probability here of 982 who died. These are men who died. 221 died from some heart disease. Of the 982, 334 had a parent who had some heart disease. Of the 334 whose parent had some heart disease, 111 died from some heart disease. And if we randomly select a man from the group, given that neither of his parents had some heart disease, we want to find the conditional probability that the man died of some heart disease. So first of all, just thinking about the information we're given, if I say H is that the man had some heart disease, and I'll call R is that the man had a parent with some heart disease. What we're given is the probability of H having heart disease is 221 out of the 982. 334 had a parent with some heart disease, so the probability of R is 334 out of 982. And then we're told of the 334 who had a parent with some heart disease, so I'm only interested in that group, so I'm conditioning on them. $111 had some heart disease themselves, so there's a conditional probability. And the probability I'm trying to find is the probability that, let's see, so given that neither of his parents had some heart disease, so given our complement, what is the probability that the man died of some heart disease? Now, yes. Oh, sorry. Let me scooch that up. Thank you. So one of the ways that I can approach this problem is to start off by thinking, okay, if I want to find this probability, the probability of having some heart disease is equal to the probability of having some heart disease given that a parent had some heart disease, and that is given to me, times the probability that I had a parent with some heart disease, plus having a parent with some heart disease versus not having a parent. Those are mutually exclusive and exhaustive. So I could also write this as the probability of having heart disease given that you do not have a parent with heart disease times the probability of not having a parent with heart disease. At this point, I know all of these values are given to me, except this one that I'm trying to solve for, because I know that this is 1 minus the probability of having a parent with some heart disease. So at this point I could rearrange and I could solve for the probability of having heart disease given that you did not have a parent with heart disease using this law of total probability. So just an example of how we can partition this event, having heart disease, into the chance of having heart disease if you have a parent and having a parent with heart disease, plus the probability of having heart disease and not having a parent with heart disease. Anyway, just a little note, because that is a super useful tool to use when we're trying to work on probability, and it's something that, as I say, I think the book really just sort of mentions it very glancingly, and I just wanted to point it out. Let's see. The other question that I want to talk about is the one that was asked about on the discussion board, was the one 1.4-16. This is the one where we've got an urn with 5 balls in it. One of the balls has the word win printed on it. The other 4 have the word lose on them. And you're playing with another player. You're taking turns selecting balls at random from the urn. The first person to select the win ball is the winner. So if you draw first, we want to find the probability that you will win if the sampling is done with replacement first of all, and then without replacement is the second part. So we'll start with the with replacement. So we can think that the probability that you win is going to be the probability that you win on the first pick. Now, the second pick is going to be the other player, plus the probability that you win on the third pick, plus, okay, if you don't win on the third pick, the fourth pick is going to go to the other person. You could win on the fifth pick, and so on. Because we're sampling with replacement, it is theoretically possible that no one could ever win, right? That never get that win ball. Very unlikely to go on for a super long time, but it's possible. So we're trying to figure out the probability of winning in this situation. We're going to end up with an infinite series that we have to work with. So first thing, say, okay, well, let's start thinking about what's the probability that we win with the first pick. We're randomly choosing. There are 5 balls. One says win, so the chance of winning on the first pick is 1/5. So to win on the second pick, on the third pick, sorry. That would mean that nobody won on the first 2 picks, right? So a loser ball was drawn on the first 2 picks, and that the winner ball was drawn on the third pick. Now, because we're sampling with replacement, the probability of choosing the winner ball doesn't change, and each pick is independent of what's happened before. So this is the probability of lose on the first ball and lose on the second pick from the other person and winning on the third pick. which because we have independent events, it's going to be 4/5 chance of losing on the first one, times 4/5 on the second one losing, times 1/5 on the third one winning, sorry. And just to go one more, probability of winning on the 5th pick. Okay, so here, the first 4 picks would have to be losers. So it'd be lose on the first, and lose on the second, and lose on the third, and lose on the fourth, and a win on the 5th. So here we're going to have 4/5 times 4/5 times 4/5 chance of losing on the third times a 4/5 chance of losing on the fourth times a 1/5 chance of winning on the 5th. So in general, we've got 1/5 times, we can think of this as like 4/5 to the 0 power, right? No losers. Here we've got 1/5 times 4/5 to the 2nd power. Here we've got 1/5, one winner, times 4/5 to the 4th power, because there are 4 times losing. So if we think about this pattern continuing off to infinity, then the series we're going to be looking at is going to be the sum of 1/5 times 4/5 to the 2 times k, right? 2 times 0 would be 0, 2 times 1 would be 2, 2 times 2 would be 4, right? So I'm getting the same pattern as k goes from 0 to infinity. So this is a geometric series. You can think of this as being 1/5 times 4/5 squared to the k power, right? So when we think about what this is going to converge to, it is going to converge to 1/5 divided by 1 minus 4/5 squared, which should give us 5/9. Yes?
Why is it 2K?
Why?
Does it mean if you were to win on the second?
You can't win on the second pick, right? You can win on your second pick, but it's really the third
you
pick.
Pick first?
Right, you pick first, then the other player picks, then you pick again. So you can't win on the second pick, or the 4th pick, or the 6th pick. You can only win on the 1st, the 3rd, the 5th, the 7th.
Okay.
Okay. To do it without replacement is actually it's a little bit different, but it's similar. The idea here would be that without replacement, so think about this, we've got sort of different possibilities now. We're not replacing it, so you could win on the 1st pick. You could win on the 3rd pick. And you could win on the 5th pick. And there's really no chance that you could do anything else, because by then the 5 balls have all been chosen and there's nothing left, right? Because we're sampling without replacement now. The difference here is that now what happens in each of the picks is no longer independent of each other, right? So the probability of winning on the 1st pick is still 1/5. The probability of winning on the 3rd pick is a little more complicated, right? Now I have to say, okay, well, winning on the third pick would require is the probability of winning on the third pick given that we had a lose on the first two. Right? Times the probability of losing on the first two. Right? So given that we've lost on the first two, well, that would mean that there are 3 balls left, right? Because two of the losers have been taken out. So there'd be a 1/3 chance of picking the winner, given that the first 2 are losers. Now we need to figure out the probability of losing on the first 2. Think of lose 1 intersect with lose 2. The first pick was a loser and the second was a loser. This is the same as the probability that the second was a loser, given that the first was a loser, times the probability that the first ball was a loser, given that the first ball was a loser, the probability that the second is a lose now is there were 4 balls left, so it would be 3 out of the 4 balls would say lose on them at that point. And the chance that a lose ball was chosen the first time would be 4 out of 5. So we can see that this comes out to does that make sense? Should I screw something up? Let me just look at my notes. 4/5, 3/4. Yep, that looks right. Okay. And then we can keep going and do the same kind of process for the third possibility, which is to do the 5th pick. But the idea is there. So that's really sort of how we approach it. We have to break it up into pieces like that. Right, to think about what's the probability that we lose on each of them. And they do, because we're sampling without replacing the balls, the probabilities change. So we have to think of them conditional on what's happened already. Okay. Are there any other questions that anybody wants to discuss or anything that needs to be more clear? Okay. If not, so next week we will start Chapter 2, which is Module 5 is the beginning of Chapter 2. Chapter 2 focuses on discrete distributions, so distributions, probability distributions that are giving probabilities for discrete random variables. The first section of this Module 5 is going to talk about discrete random variables of the random variables of the discrete type is the top title of it. I'm having trouble talking today. In any case, that should give us an introduction. It will teach us to sort of distinguish between discrete versus continuous random variables and how to work a little bit with the distributions. Hopefully some of you have seen some of this material before, working maybe with binomial distributions in other courses. If not, and you need a little extra help, don't hesitate to get on the discussion board and ask. Also remember that I do have office hours, both online and in my office on campus for people who are here. And they are listed on Blackboard under the Office Hours tab, so don't hesitate to use them. I haven't seen too many people in yet, and I'm happy to have people come to get any help you need. All right, have a good day.